What I'm going to do now is go through a number of examples and to illustrate design and coding techniques with Verilog RTL. The first example is a simple example. This is actually your homework 0. This was the class solution at least. You might recall what we have here is we're counting the number of times a certain sequence appears as a number, and we're accumulating that count on count. If we get overflow, we stop the count. So I asked you to do this as a hard design down to the bit level, almost to the bit level, without using RTL. Now what we're going to do is translate this into RTL. And of course this is relatively straightforward. What we have here are 2 registers. So what we need to do is take the input logic to those registers, which are muxes, and code them together with the register assignment. So we'll have an always at POS clock block or 2. However, there's something, complexity here. We have to assign cout and sum like this in order to get the overflow. So that means that this block to the left here will have to be its own logic block. We cannot just combine it in with count. So we're going to have 3 chunks of logic, 1 chunk for count and its input mux, 1 chunk for clock and its input mux, and another chunk for this for this gate and the adder. This is the code here. What you see I've actually done is combine the 2 flip-flop blocks together into one procedural block. We can do that, and that's quite common to do that. It saves code, it's more concise, though it does make for longer procedural blocks. So we have here, when start is high, count goes to 0, else count goes to sum coming out there. And this is to assign overflow. I did this as a case X statement, so it's because it's a little more complicated. Case X on start and overflow. If both are 0, overflow goes to cout. If overflow is 1, keep overflow as 1. If start is high, clear overflow. If they're both high, clear overflow because start had priority. And this default here was simply to assure is not really necessary, particularly as this is a POS edge clock block. But it does propagate don't cares. Then I have this logic here, which it is continuous assignment, assign concatenation of cout and sum to produce the 9-bit result on the left that matches the 9 bits that come out of an adder. All I did here was a unary reduction operator on the bits of in, just directly inverting the 2 bits that had to be inverted so that we could do the count so we could count, I believe it was 5s if I remember right, in the correct sequence. So this is an example of translating logic into code and just illustrating a straightforward way of doing that. Here's another example. This time I have a truth table. What I have here is 3 bits from some other register, 3 other bits coming from somewhere else, and I've got to assign these control lines as drawn here. And this is a truth table. That's all it is. So when you get a truth table, what do you think of coding this as? You code it as a case statement. So here's the case statement coding that truth table. To make it easy, I've concatenated add sub and an OR together to create a new variable called out. This is just simple string substitution. When I'm assigning out here, I am assigning to these 3 bits. This just made it easy from a coding perspective, rather than writing this out every time in the right hand side. So it just saves for type, means we have less typing. Then I just code the truth table. When those 3 bits of IR are 1, out is equal to 1, 0, 0. When the 3 bits of IR are 0, 1, 0, out is equal to 0, 0, 0. When it's 1, 1, we then look at in, so I have a case statement, nested case statement on in. When in is 0, 0, 1, out is appropriate, so on. Then I have my defaults to cover all the other cases. This is combinational logic, so I have to make sure I cover that I assign the output for every possible combinations of inputs. So I have the default here, out equals X, and the default here, out equals X. This is important in order to capture the rest of this truth table completely and to not prevent having unintended latches. By the way, you'll note here that I did out with a small o. What would actually happen with that? This actually ended up being flagged as a syntax error because this small o out would not have been declared. Remember, the Verilog is case sensitive, so I'd have to go. This would be flagged as an syntax error for an undeclared variable, and that's how I would catch it and go back and change it to capital O out. Here's another example of combinational logic, this time using operators. I want to build this general shift rotate unit. I'm going to have logical shift left and right, sign shift left and right, keeping the sign bit, and logical rotate left and right. I'm going to do this in Verilog 95, just make it a little more complicated. A is the input, B is the output, rot is these 3 bits here, count is how far we're shifting or rotating. Again, a good way to think of this is building as a case statement based on rot. 0, 0, 0 and 0, 1 are simple shifts. 0, 1, 0, sign shift left. I want to keep the sign bit. So what I did was a temporary variable C that I did the shift in. I substituted the highest order bit of C with the original sign bit. 0, 1, 1, I want to sign bit shift right, keeping the sign bit. So what I did, I've shown this before, I made 16 copies of the sign bit. Syntax error here, this will be square brackets. And concatenated that with the 16 bits of the original of A. So no matter how far I shift to the right, I'll still have the correct sign bit. The rotates we've seen before, make a copy of A, so this is total 32 bits wide. No matter how far you shift it, at least within 16 bits, and since count is 4 bits, you can only shift it that far. Then this will rotate the high order bits or the low order bits in as appropriate. Again, I've illustrated this in the Verilog 2 notes. The default B equals X is just a good habit to get into. Remember, it makes sure that don't cares propagate properly on initialization. It also just catches anything in case, in case here I have a problem that I just realized, and that is that I've assigned C in only one place. That will lead to, of course, what? Unintentional latches. So I need to assign C. Let's go and do that up here. C equals X. I'm just using spaces instead of proper way of I normally wouldn't do this. I do this on the next line, but I'm running out of space a bit. So that makes the example more accurate. So this would have been caught. Here I accidentally built an unintended latch. This would have been caught if I had after the read and synopsis, I would have seen that I had latches and C was the latch, and I would have realized why and fixed it at that point. Here I just fixed it ahead of time. Next we have a serial demux unit. What I want to do here is when new packet is high, I'm going to read in data in. This tells me how I'm going to demux the next few bits, next few bytes onto these outputs here. So the idea is I send a packet there, then a packet there, then a packet there. So the 7 indicates where I send the first packet to port 7. The 3 indicates how many cycles I'm doing this for. I'm doing this for 3 cycles, 1 cycle, 2 cycle, 3 cycles. Here's another example. Here I'm going to have a packet consisting of 3 data ins. The first one indicates where the first one goes to port 0 and how many words I'm going to send through. I'm going to send 2 words, 88 and 99, to port 0 and port 1. So the idea is I've got a demux here, and how that demux is directed is indicated by the first byte of the packet. The succeeding bytes of the packet are actually sent out to the demux ports. That's a fairly quick explanation. What I suggest you do is actually pause this and read this so you can understand what's going on. Next, I sketched the design. I did that as a pencast. So again, I'm going to say here, C pencast. To see the sketch of the design. And as you can see, I during that design, I had to rethink my strategy even while I was developing it in order to get a correct design. This is the solution. These are just the header stuff, the declarations. Here's the content of the design. The guts of this, remember, is on the left here. I've got the muxes going to the data out ports. If P is high and that particular decode line is high, then I want the data int to go to that particular demux. Otherwise, I want 0 to go to that demux. Here is the delay register on data int. Here is the port and count registers in one always POS edge clock statement. Here are the muxes in front, 2 POS edge clock statements, sorry. Here's the mux in front of port. Here's the mux in front of count. Here's the go line. And here's PE, which is the delayed go. And all I'm doing again is just translating my design to chunks of code using my knowledge of how to do this. The other thing I didn't point out, this is a sign statement. These are producing the 8 decode bits. I'm doing this in much the same way as I did the row decoder for the register file. I take 1 and shift it left by the port count in order to shift 1 into one and only one of these decodes. So that completes that particular example. Again, I've gone through this fairly quickly. Feel free to go back over it so you can understand how this was produced. Next one is the Fibonacci sequence. The concept here is quite simple. I've got n coming into the design. When n changes, I want to calculate the Fibonacci number. That is the sum of I equals 1 to n. I'll give the example here, n equals 3. I want to calculate 1 plus 2 plus 3 equals 6. And again, I want to detect that a new number needs to be calculated by detecting if n has changed. By the way, Fibonacci did not invent this sequence. He stole it from he didn't steal it. He discovered it independent from the Arabs and popularized it, along with many other things, including the invention, I believe, of double entry accounting in the early Renaissance in Italy. Okay, so first step, of course, is to sketch the design. I've got a pencast in which I've done that, including explicitly separating control for data path. ask you to refer to that pencast, please. Then we translate that design into Verilog. This is that translation. So what do we have here? We have the data path on the left. This is the mux and register for the Fibonacci accumulator. This is the mux and the register for the counter, the down counter. This is the 1 flag. This is the clock delay producing nprev. We're producing the equal flag. Then we have our finite state machine. I just copied this from the template. Right. State equals next state except on reset. It's a more machine, so the outputs are associated with the states, so I use the more machine template. Fmux and Cmux is 0. Then determine the branch. If equal, go to S1. Next state, just go into S2. State S2. Stay in state S2 until 1 goes high. Again, more machine, Fmux and Cmux are 2. Need the default here to prevent unintentional latches and to make sure and to catch the illegal state. State S3 is an illegal state. Now I just realized again I have made some latches. What have I made latches? Fmux and Cmux. So I'm just going to make those both 0. Actually, I'm making don't care. Alright, so that prevents those from being latches. I then have my parameters for my states. I misdeclared state there. State is 2 bits wide. I haven't bothered putting in the synopsis directives regarding FSM optimization. Such a small FSM it actually wouldn't be worth it. I declare count, nprev, and fib. I worked out the fib needs to be 7 bits long to account for the maximum possible value of n coming in. Okay, I've now gone through these examples fairly quickly. And again, actually the key information in the last 2 examples is in the pencast. So I hope you actually stopped and looked at those before going on to looking at how the Verilog was produced. And I hope this was useful to you. Thank you very much for your attention.